I ran into you downstairs and I was in the middle of a 2-hour-long faculty senate meeting, and I was like, I have to go to the bathroom so quick, so I couldn't even like process who I was running into. And I was like, I feel bad. I probably looked so cold.
No, you can put your hand on it.
I was like, excuse me. She's like, hey. Anyways, I hope that that is not one of your fears in this class, is that your professor is going to be cold to you and brush you off and not say hello. But I am curious if you guys felt like sharing any of your goals or your fears for this class. Elliot?
Actually do like a very substantive pre-reading before we get into class.
That's your goal?
Yeah.
Yeah.
Don't usually do that. I think this class warrants it.
That's fair. That's fair. I will say one thing about pre-readings, and that is we're not going to cover an entire chapter in one class period. But you never know how much of a chapter we're going to cover in one class period. And so an in-depth reading can always be good. I would say especially while you're doing homework, to try and find definitions and examples to support yourself. But before you come into class, skimming and scanning is almost better. What words would you have highlighted? What words do you think need definitions written down, you know? And then sometimes going back and re-skimming and recognizing what things did we cover in that lecture and looking ahead at the things we're gonna look at next. I do wish that I could direct you guys a little bit better and say, this is how many of the pages I think we're gonna read. This is how far I think we're gonna get. And actually, to that point, I have something to show you guys that I'm planning to add to our Canvas course. But I hope that you guys all share that goal. Try to get into the textbook before you come into class and get confused about stuff so that when I bring it up for the first time, it's actually addressing some questions and not just creating the confusion. Other things that you guys would like to share? Yes, Mel.
A long time ago, I had a roommate that took OChem at University of Utah, and they would come home crying quite a bit.
Yeah.
To not be emotionally abused by the OChem class.
Yes. And I appreciate you saying not being emotionally abused by the class and not by me. But I also hope that you guys can actually leave organic chemistry with a somewhat positive experience and not just a negative experience. Great. That's a good goal. Yeah. Protect your heart. What else? Mo, was that a goal or a fear?
Oh.
Yeah. Indigo.
I would say my goal is to not only pass the class, but also understand it.
I love that goal. Don't just pass. Don't just get the grade you want, but walk away with some understanding. Walk away able to tell somebody what they can expect from organic chemistry beyond just emotional abuse. That's great. Goal setting is really important. If you don't have strong motivation, this class can burn you out super fast. And with the wrong motivation, too, you can lose energy halfway through the semester and find it really hard to finish strong. So I want you guys to spend some time on your own, really thinking about your goals. Some of you have bachelors already. Some of you are in graduate programs already. Some of you are taking this class because you're not sure which route you're going to go down. So if you have your motivations, great. Talk with your classmates about them, about your motivations. Inspire motivation into others. And if you are someone that's still seeking that out and trying to name your own motivations, talk with other people. Figure out what their motivations are. Get inspiration. Okay. It's nice that nobody shared a fear, but I guarantee you, you all have some fears lurking in the back. Like, I'm not going to understand what's going on. Everybody else is smarter than me. My question is stupid. I shouldn't ask it in class. And I just want to make sure that we're all on the same page. If you have a question, somebody else probably has that question. you should address it. I do think that I've adapted my teaching style over the few years I've been teaching to try and pre-address the questions that I've seen come up a lot. And then that just creates opportunity for new questions. So ask the questions you have. If you feel like you're falling behind, talk to me so that I can try to give you a targeted game plan on how to catch back up, what to work on. But if one of your fears is not being able to catch on to the material as much as everyone else, then you should get to know the people around you, get to know everybody, sit somewhere new every day, and build a study group. Get to know those people and work with them, learn from them. It can be really beneficial. All right, one thing that I'm trying to do to mitigate your fears is give you an idea of what I'm trying to teach. So on your unit tests, the multiple choice questions are essentially set up to target one of your learning objectives. And oftentimes those question banks come at those learning objectives from different directions, but they are mastering the same concept. So over the weekend, I put this document together and I've added it to the top of Unit 1. And I will try to do that again this week so that you have it in advance of Unit 2. It tries to phrase your learning objectives as skills that you have at the end of it, which means if I set a problem down in front of you, this is kind of how you would be able to tackle that problem. So it has action verbs in them. And there's a whole document with like 1,000 action verbs, and it's really hard to choose the right one. But I did my best. So we have looked at formal charge and bonding patterns. It is an important role for you this semester to know formal charge, bonding patterns, especially when it comes to whether lone pairs are shown and formal charge is not, or whether a formal charge is shown and lone pairs are not, and being able to relate those. So bonding patterns there, it means not just bonds, but non-bonding electrons as well. The reason I really wanted to put this together was because we have 2 class periods before your unit test, which isn't fair, right? Because we've only had 2 class periods, and it feels like it's going too fast. So I needed to make a very clear checklist of what I needed to teach you in these next 2 classes, and these are our goals. I'm hoping to get here by the end of today, and that might feel like a lot, but these are all relatively related topics, so they're going to bleed into each other pretty well. I also want to give you guys a chance for active learning, so rather than me just putting everything on the board that I think will help you understand these, pause, do some practice problems where I come around and give you some feedback and you get to actually apply it. That's the goal. Which means that Wednesday, we're planning to do all of these. And again, these are all fairly related concepts. A bit challenging, to be sure, but we'll try to break them into 10, 15, 20-minute blocks with opportunities to apply things during them. The reason that I do want to really power through and get through these 2 sections to finish up our unit is because having your unit test this weekend, and I'm just trying to reiterate this, having your unit test this weekend sets you up to know what a major assignment feels like in this course before the drop deadline. I hope none of you have to drop. I hope you can all stay with me all semester long. But I know that some of you have a very busy life right now, tons of credits, job on top of that, taking care of your family, and you might be thinking, I don't know, I could maybe push back OChem 1 and retake it another semester. So I'm trying to make sure that we stay on track with this calendar, and that you guys have the opportunity to make the best decision about this class. Any questions? Okay. I also wanted to have a handout today, but my meeting earlier kind of prevented me from making it. So I'd like to implement some handouts that I can give to you guys. That's one piece of feedback I get all the time, is that I put too much on the board and then it really slows down how much you guys can copy down. So we'll see if we can do that. All right. So last week we looked at formal charges. I want to see if you guys did your homework. Given that these all have the appropriate number of lone pairs and bonds shown, can you provide the formal charges, if any? You can feel free to copy them down, but I would like to just kind of pick on anybody that can do it. First one, any formal charge missing? Belen. So all lone pairs are shown. It's not neutral. Okay. This is a +1 charge. Good. My oxygen atom. How do you know it?
Because you have oxygen 6, you've got the lone pair and then the 3 bonds.
Did you do the math in your head?
I mean, kind of, but at the same time, I was trying to draw this chart a bunch of times. So
Good.
to me, that was
So
like,
part of it is recognizing the bonding pattern. Good. My nitrogen, formal charge. In the back, Nicole. -1. Nitrogen likes 3 bonds. So nitrogen with 2 bonds, that means it has too many electrons of its own, negative charge. And my halogen.
Is that +1?
This is a +1. Halogens only like 1 bond. So similar to oxygen having 3 bonds, this halogen has too many bonds. It's sharing too much. And that means that it is positively charged. Good. That's where we ended off last week, right? I didn't get you guys into hybridization. I filled out that table and sent you home. So this is one of my favorite topics. Orbitals. First of all, can anybody define for me what orbitals are? Have we talked about this? I don't think so. No.
Orbitals are where electrons would most likely be.
Where electrons most likely are. Okay, that's a good start. Can we add to it?
There's like 3 main types, like the S, P, and D.
Okay, there's types of them: S, P, D, and F. The F orbitals are the ones at the very bottom of the periodic table. You don't talk about them a lot in general or organic or inorganic chemistry. Physical chemists, theoretical chemists are the ones that talk about F. But actually, there are G, H, I, J, K, L, M, N, O, P, Q. I could keep going, but it doesn't matter. There are orbitals that keep going. These are just subsets of orbitals that are differentiated from each other in some capacity. They started interesting, S, P, D, F, and then the alphabet just goes on from there. So the types we'll be considering the most are S and P as atomic orbitals, and those are going to play into our hybridized orbitals. So Mel said something where electrons are most likely to be found. So electron orbitals are 95% of the probability region of where electrons are. We cut off the remaining 5% of that region because it extends to infinity. There is a non-zero probability that one of your electrons could be on the moon right now, which means there's also a non-zero probability that all of your electrons could be on the moon right now. Odd, right? So it's useful if we think about 95% of that probability, because the rest of it is just less significant. this place where electrons can be, it's not just this arbitrary thing. These are mathematical equations. So just like you can describe a wave in the ocean, right? Where is that wave most likely to be? Well, part of that wave goes up, part of that wave goes down, part of that wave has a curve that looks like this. You can create a mathematical equation that describes that region. So electron orbitals have size, shape, and orientation. Is it oriented? Well, spherically, has no direct orientation. Is it oriented vertically, horizontally, in and out, X, Y, Z, things like that? All right. So the atomic orbitals that you all hopefully are familiar with in increasing energy, the 1s, the 2s, the 2p's. And I'm going to break down the 2p's. 2px, 2py, and 2pz. Orientation is distinct from those 3p orbitals. And if we go up another shell, we get 3s, 3p, and 3d. This isn't something that we're actually going to be tested on, but I like to reiterate this once I remind you that electron orbitals are math equations. All orbitals of a given shell have the same number of nodes. A node is a place in that mathematical equation where electrons have 0 probability of being found. It's also a place in that mathematical equation where the description of the electron moves from being described by the math equation with a plus to being described by a minus. So these math equations begin with plus minus a bunch of math. And in some regions, it is only plus. In some regions, it's only minus. And that's where we get our shading and our non-shading. So the 1s orbital has 0 nodes. It's completely spherical. In the second shell, the s orbital gets a spherical node. So this is like having a volleyball inside of a tennis ball. The volleyball part of the orbital is a mathematical equation that begins with plus. Then there's a node, and then there's the basketball part of the orbital that begins with minus. So it's hard to draw, but there's a ball inside of a ball, a spherical node. The p orbitals have angular nodes instead. It splits the orbital in two. Px, let's draw it along the x-axis. Py, we'll draw it along the y-axis. And Pz, we draw it along the z-axis. Same shape, same size, but distinct orientations. And they all have one node. In the third shell, how many nodes does the 3s orbital have? 0 nodes, 1 node. 3s, 2 nodes. How many nodes does the 3p orbitals have? 1 node, 2 nodes. Now, the s orbital has spherical node, 2 spherical nodes. The p orbital has angular node, spherical node. And the d orbitals that get introduced, the 3d orbitals, they have no spherical, but 2 angular nodes, which is why the d orbitals look more like flowers. They've got 2 nodes cutting through them. So each time you go up up a level of shell, that orbital from below gets a new spherical node. It always maintains the same number of angular nodes. These are our shapes, the s and the p orbitals that we're going to be dealing with predominantly. These orbitals, best described as atomic or hybridized? these orbitals. These are atomic orbitals. These are the orbitals that you would expect electrons to be in if you studied a hydrogen atom, or if you studied an atom that's being made in a star and flung out during a supernova. But these orbitals have a ton of relationship between electron pairs. If you put electrons into these orbitals, those electrons start to repel each other greatly. And especially if you want to create bonding between atoms, the electron pairs in orbitals like this create super high energy strain. So, electron orbitals, which are mathematical equations, kind of like waves, can be combined as mathematical equations in the same way that waves can. If you have constructive interference with waves, you get bigger waves. Destructive interference with waves, they cancel each other out. So this is how we get hybridized orbitals. First, imagine we take S and P. This is the overlap of an S orbital and a P orbital. Now keep in mind, the nuclei are focused at the center here, so this really looks like this. Which P orbital have I drawn up there? Kira, just based on what I drew here, which P orbital have I picked? Right. So because my P orbital has one specific orientation, I'm actually going to get two new orbitals out that have one specific orientation. So this is going to give me a new orbital. And actually, I'm going to redraw this because I don't think it's exaggerated enough. These are new orbitals that are called sp orbitals. They are not s orbitals. You'll notice they're not just circles or spheres. They're not p orbitals because their lobes are not proportional sizes. I've got this tiny lobe on one side. That is the result of this destructive interference between shaded plus and unshaded minus. And I've got this giant lobe on the outside, so that's the result of constructive interference, plus and plus, or minus and minus.
Wait, are the little dots the tiny ones?
Yes, that's right.
Okay.
These are lobes. Now, I draw them separately, but notice that I've drawn them linearly. But in reality, they take up a little bit of the same space. The nucleus sits right here. So this is actually better drawn like this, but is that clear to you at all? Kind of looks like cartoon eyes going cross-eyed. Doesn't mean anything. So I'm just drawing them separate so you can actually see their shape. But in terms of orientation, they have some overlap. How would you describe the relationship between these two orbitals? How are they aligned in space relative to each other? Yeah. How many axes was I allowed access to? Just one, the x-axis. So these orbitals are aligned linear to each other. That means that this new atom, which has hybridized S and P, has linear geometry. These hybridized orbitals, they like to give head-on overlap with other orbitals from other atoms. So this allows two sp orbitals, gives two sigma bonds. Sigma there represented by the Greek letter sigma. But my atom still had two other p orbitals. So that means that I can have up to 2 pi bonds. I'm not required to have 2 pi bonds, but I can have up to 2 pi bonds. These things work forward and backwards. If you recognize something, a central atom that has 2 pi bonds, it has sp hybridization. If you recognize something that has sp hybridization, it has a linear geometry. If you recognize something with a linear geometry, it is sp hybridized. If it has a linear geometry, it has 2 pi bonds, most likely, or maybe a positive charge. Hybridization, make a little bit of sense. Definitely a refresher, right? What's our next case? How else can we hybridize these atomic orbitals? sp2. Now I'm not just taking s and px, I'm also taking py. And it looks really like it makes a lot of sense when I draw it like this, right? Because again, they're all centered over the nucleus. And what I'm doing is taking the mathematical equations that describe them, and I'm summing them together. Regions that have opposite shading, regions that are out of phase, cancel each other out. Regions that are in phase, sum each other up. Now, I took in 2 orbitals before, and I got 2 orbitals out. How many orbitals should I make with sp2 hybridization? Yvonne? 3. 3 orbitals in, 3 orbitals out. But these orbitals are hybridizing for what reason? Why are the orbitals even going through this process? I said it a little bit earlier. What is the point? Well, if there's no point, we should just move on. It's to minimize electron repulsion. So I can't just draw these orbitals in any orientation that I want. I need to draw them in a way where they minimize their repulsion from one another. Along that px hybridization with sp, minimized orientation would be straight away from each other. What is the furthest that I can orient 3 orbitals away from each other? What shape does it make? A triangle. So I can have one orbital oriented straight up, one that's down to the left, and one that's down to the right. They orient each other as far away from each other as possible. It's not 2 of them linear and 1 of them vertical, right? By the way, how many axes do I need to have access to in order for them to spread out like this? 2. And how many axes did I hybridize from my p orbital? 2. I hybridized py and px. That's a plane. And so now my new sp2 orbitals exist only in a plane, but they actually define a plane. Okay, so just like before, if I wanted to draw these all on top of each other, it looks a little silly because they kind of push through each other and they create this little shape. So let's describe the geometry of an atom that can bond with sp2 hybridized orbitals. You know this. Yep, to represent the triangle, we call it trigonal or trigonal. Planar, because they exist in a plane. How many sigma bonds can this atom make? 3, 1 with each of its hybridized orbitals. And how many pi bonds can it make? Just one. It doesn't need to make a pi bond, but it can make a pi bond because it has an unhybridized p orbital. It has a leftover p orbital. Okay? Our last form of hybridization. What is it? sp3. So here we take the s atomic orbital, the px atomic orbital, the py atomic orbital, the pz atomic orbital, the circle in front of a circle. We overlap them all together. Bet you can't even see the pz in that one. Now, how many axes do I have access to? 3 axes, 3 dimensions. So my new orbitals, the sp3 orbitals, can take up 3-dimensional space, which means it gets really challenging to draw it. So here's actually how I'm going to model it. 2 lines that are in plane, and they make this axis, this vertex. And then another 2 lines that are in plane with each other, but are perpendicular to those 2 lines. So one of them comes out towards you, one of them goes away. I'm going to represent that with a wedge coming towards you and a dash going away. That represents that 3D geometry. And now if I wanted to, I would just show what those orbitals look like along that spatial arrangement. Something coming towards you is going to block that other part of the lobe. Something going away from you is also going to block that other part of the lobe. Did you guys know you were signing up for art class? That's what it should feel like. We are looking at perspective relationship here. What geometry do we call this? Tetrahedral. Coming from the word for 4-sided face. So in my opinion, the least intuitive geometry, or the least intuitive name for geometry. How many sigma bonds? 4 sigma bonds. How many pi bonds? What? Do you see the trend? 2, 1, 0. What you need in order for a pi bond should start to become evident right now. An sp atom has left behind 2 p orbitals and can make 2 pi bonds, p and pi. sp2 has left behind just 1 p orbital, can make 1 pi bond. Tetrahedral doesn't have any p orbitals remaining, cannot make any pi bonds. So this is going to help us understand what types of orbitals make what types of bonds and how that can infer back to hybridization. But first, I do want to point out something about perspective. This isn't inherently an art class, but that doesn't mean that you're allowed to break the rules of physics. If you scroll down on our homepage, you'll find this link to SimOtter, Symmetry at Otterbein University. This is a great website for visualizing 3D molecules, except that they're a little bit limited with their selections. There's also, oh, I never added it. There's also a website called MoleView. I'll add it to our homepage, where you can actually build molecules. Now, what I want to look at with you guys is a simple molecule, methane, which is sp3 hybridized and is not currently arranged in a perspective that agrees with this. What you should see are two bonds that are coming towards you, in other words, two wedges, and two bonds that are going away from you, two dashes. That is a valid way to draw its geometry. Two wedges, two dashes, bisecting one another. This is the perspective that I have on the board. In plane with each other, in plane with my screen, something coming towards you, something going away. Now, to be fair, if this were actually in plane with the board, it would look a little something like this, where you can't actually see the atom in the back. But what good is it to me if I can't draw that dashed bond? I need to see that bond. So we actually take this perspective and we shift it just a little bit. We tip it on its side. Now you'll notice what's going back is kind of on top, but I could have shifted this way, and now what's going back is just on bottom. So a little exercise with you guys in drawing perspectives. Wedge on the bottom, dash on the top is exactly equal to wedge on the top, dash on the bottom. Those three lines, exactly equal to. These are not different. They're just slightly different shifts in your perspective. But here's what's wrong. Here's what I get from students semester after semester. They'll give me something like this. That is like drawing the Eiffel Tower with its base coming up and then its point sticking at you. It just doesn't physically make sense. Like, as weird as that image is in your head, that's how weird that is. Let's try to do it. Okay, let's get two things that are in plane with each other and create this angle. All right, I've got that. And now, let's have something that comes towards me come through it, and something that goes away from me go behind it. I can't. Because the thing that's going away from me is already behind it, and that leaves the thing coming towards me also on that side of the vertex. If I push this thing coming towards me, this wedge, over to the other side, notice that these are not in the plane of the board anymore. They're now dashed as well. So this doesn't exist. What does exist is something like this. But I think for sake of detail that's required, you can understand why we don't draw it from that perspective a lot. All right. I am going to try and teach you this semester on how to utilize all of that stuff, okay? All right. I want to dive into these bonds a little bit more, sigma and pi. But before we do, I'm going to take us back to those atoms that we had drawn up here at the start. I'd like for you guys to tell me their hybridization, their molecular geometry, and rationalize how many sigma and pi bonds they have. Rather than doing all of them, I'm going to assign you guys, okay? So, carbon, oxygen, nitrogen, halogen, carbon, oxygen, nitrogen. That's just what we'll do. I don't know why I switched my oxygen and nitrogen. I hope that's not confusing you guys. They're not in electronegativity order. They're not in periodic table order. My bad. Anyways, determine their hybridization. Determine their molecular geometry. How many sigma and how many pi bonds they have. Up to your point, Sarah, it can make a pi bond there. It's currently not making a pi bond there, which is why it has that positive charge. So that list, that's what I'm trying to illustrate there. It can make up to one pi bond. In here, it actually has one. You'll see it. Yep. It'll have two lines going to the next thing, a double line. Right?
Because, like, if I fill this spot, right, then it wouldn't have any.
Oh, well, it doesn't have these orbitals. You told me it's sp2, and the number actually goes as a superscript rather than a subscript. I'm not sure exactly what the difference it makes, but that is just which means it doesn't have s orbital anymore, and it doesn't have p orbital anymore. It has three orbitals that are sp2, and it has one orbital that is p. If that p orbital was filled with bonds, with electrons, then you would see it. It would make 4 bonds. But as it is, that carbon only has 3 bonds. So it must only be sp2 with no pi bond. The capacity for a pi bond, but no pi bond. All right, are you ready? Carbon. I've got 2 groups. Why don't you guys tell me hybridization and molecular geometry?
SP2 and trigonal planar.
Good. sp2 trigonal planar. Carbon, oxygen, nitrogen, halogen. Carbon. Number of sigma bonds and number of pi bonds on this atom.
3 sigma bonds.
No
No pi bonds.
pi bonds. How did you know that?
Because there's not a double bond to the carbon. I don't know if that's the right way, but
That's a good way. You know from Gen Chem that when you have multiple bonds, each bond contains sigma, and every bond additional is pi. First of all, this atom only has 3 bonds. And we said that this will have 3 sigma and 1 pi. So you had a couple of options. You could have said, they're all sigma, there is no pi. Or you could have said, maybe there's 2 sigma and 1 pi, how am I to know, right? But remember that electrons want to spread out as much as possible to minimize their repulsion. And that spreading out is going to be into the hybridized orbitals. So this positive charge, that's an unoccupied p orbital. It has the capacity for a pi bond, it's just not currently in a pi bond. Okay. Oxygen, why don't you guys tell me molecular geometry and hybridization? Okay. And? Trigonal planar. Now, how did you figure that out?
We did it based on the orbitals.
Okay.
So we figured out what the sigma and the pi was.
Good. Other oxygen. What did you guys say for sigma bonds and pi bonds?
2 sigma and 1 pi.
2 sigma, 1 pi. So you'll notice that I've got this double bond here. That double bond always contains 1 sigma bond. Everything additional is a pi. And then I've got this other sigma bond. Good. And that's how you guys rationalize that it was sp2. It's got 1 pi bond. It must be sp2 because sp2 has 1 pi bond. Good. So I'm going to try and illustrate this again. These are all sigma. This has sigma and pi, not necessarily those lines specifically. All right. Nitrogen, hybridization and molecular geometry. You feeling like I'm tricking you?
That one's hard.
Really?
Cause
Do you want to pass? I have another nitrogen group. Tell me why it's hard.
the lone pairs
Okay.
and the double bond. So the double bond means no matter what, it is bonded, so it's one. But the lone pairs plus the negative, I just don't know if it's.
That is hard. It's deviating from the rules I gave you, right? Good. That's okay. Let's see what you guys said.
Alright, we said it was SP because it has because of the fact that it has the double bond means that it has 1 sigma bond, 1 pi bond, and that the other 2 are unfilled. But it's also because of the double bond, like anything that we bond to on this side would most likely make the molecule linear. So that is an indication to us that it was SP.
So you think it's linear. One of these lone pairs could be oriented directly across from the bonding region, but then where would the other lone pair go? And wherever that lone pair goes, it's going to have pretty high repulsion. It's going to be pretty close to all of the other electron regions. So I don't know that linear is going to minimize electron repulsion. Did you guys say sp2 or sp, I mean? sp2? You said sp as well?
That was our first guess, and then we second guessed ourselves.
Because you saw, well, actually, none of them say just 1 sigma bond, right? So this one seems to deviate from all of these rules.
Yeah, we thought that like the empty bonds might just be an indication that there could be more bonding potential for the molecule. So I'm not sure. We weren't. This is like with the other group. Like we weren't sure which category this fell into, so we were just going based off of the shape.
Anybody else want to pitch in on what you think the hybridization is?
SP2.
sp2? What are you going off of?
Regions of electron density.
Right. So in Gen Chem, you might have learned that you can count your electron regions, and that will add up to your hybridization. For instance, 1, 2, 3, spp, sp2. Double bonds count as 1 region. 1, 2, 3, sp2. We can do the same thing here. 1, 2, 3, 3 electron regions, sp2. Now it's fair that it doesn't actually have 3 sigma bonds. It does, though, have 1 pi bond. So I would say by lack of not having 2 sigma bonds and 2 pi bonds, the 1 pi bond should draw our attention most to the sp2. And then we can rely on counting electron regions, bonding regions, and non-bonding regions to help get us the rest of the way. So sp2, trigonal planar, with only 1 sigma bond and 1 pi bond.
Okay, so when you have it written over here, like 3 sp2 orbitals, that's like up to 3 sigma bonds.
Great.
Okay.
This is not like the Bible. It's maximum.
Okay.
Yeah.
Cool.
You can have 3 sigma bonds, but that's the max. You can have 1 pi bond, but that's the max. Notice here, we had sp2, but it had no pi bonds. Right? Here, we had sp2, but it didn't have 3 sigma bonds. And now we've got sp2, and it doesn't have even 2 sigma bonds, just 1. These hybridizations take on a lot of different shapes. This is the maximum bonding pattern you can have. Cool. Halogen. sp3 tetrahedral. And how many sigma bonds? And how many pi bonds? Good. Now that halogen has 2 distinct sigma bonds and then 2 non-bonding regions. So I can't say that it has 4 sigma bonds, but imagine that it takes that non-bonding region and shares it. Now it's a bonding region. So in that way you can count lone pairs like sigma bonding regions. Lone pairs go into those hybridized orbitals. So 4 electron orbitals, s, p, 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 sp3 hybridized. Yeah, I did. Sorry.
Okay.
Thank you for catching that. It's not 3 sigma bonds. 2 sigma bonds. Oh, that red is much better than my red. Okay. Clear as mud? What can I clarify about that process?
The whole cavity orbitals thing actually made the nitrogen thing a lot more sense.
Good. So, try to get comfortable in that discomfort. This is your guideline. It happens a lot, especially for carbons, and we're going to be dealing with a lot of carbons. But for other atoms, you just have to replace lone pairs with some of those sigma bonds. And you have to recognize that not all pi bonds are complete. Now, valence bond theory is what we're going to talk about next. And valence bond theory works to take these hybridized orbitals and use them to describe the types of bonds. So I'm going to draw a molecule for us all. Tell me if you recognize this molecule once it's up here. I know the orange can be kind of challenging to see. You guys recognize this? Do you know it? Do you know what it is? It's an amino acid. It's one of the building blocks of proteins and enzymes. Not a nucleic acid or a nucleotide. Yeah, nucleotides are actually more like OChem2 material than OChem1, to be honest. Not that you can't apply stuff from it, but they're usually planar, cyclic, got a lot of double bonds going on in them. This is an amino acid. This is specifically alanine. Alanine, if I'm correct, is the smallest utilized amino acid in the body. I might be wrong. I think glycine doesn't have that CH3 group, but I don't think it's, I don't know. I'm not a biochemist. Anyways, valence bond theory says there's a lot of bonds in here. How many pi bonds are in here? Yeah, you all should recognize that pretty quick. That double line, that's a pi bond. But what makes up that pi bond? What orbitals are overlapping to give me that pi bond? No, but good try. So valence bond theory says that pi bonds are the overlap side to side of p orbitals. Which, when you take a perspective, this is an eyeball, looking down it. When you take a perspective and look through that bonding axis, what do you see? You see what looks like a p orbital. So since the bond looks like a p orbital, it's called a pi bond. Alliteration, p for pi. It says that a sigma bond results from head-on overlap. So let's say that I have two hybridized orbitals that are overlapping with each other. I've got their big ends overlapping. And if I were to take my perspective and look down this, what I see just looks kind of like this weird sphere. And I'll admit, to be fair, it would have that dark spot in the middle. But that dark spot doesn't make it look like a p orbital. So looking down the bonding axis, what does it look like? What type of orbital? It looks like an s orbital. It looks like an s atomic orbital. So we call it sigma for s, alliteration. That's the deal. If it overlaps head-on, sigma. If it overlaps to the side, pi. Once you get into d orbitals can have sigma, pi, and delta bonding. They have face-to-face orbital overlap that looks like a d orbital, delta. All right, coming back to this. This pi bond between C and O, the only one in alanine, what orbitals are overlapping to give it? Two p orbitals. So I'm going to write that as p to p overlap, p to p. This is what valence bond theory is saying. The types of bonds, sigma and pi, are the result of overlaps of atomic orbitals or hybridized orbitals. What about the sigma bond between C and O? What orbitals are overlapping to give this? Well, that C has what hybridization? Keep in mind it's got one pi bond and 3 sigma bonds. sp2. The oxygen has 2 lone pairs, a sigma bond and a pi bond. 1 pi bond, sp2. So the orbitals at carbon's disposal and the orbitals at oxygen's disposal are sp2 and sp2. Those are the orbitals responsible for creating that sigma bond. So I would like you to tell me what orbitals overlap to give the sigma bond here between C and H, and what orbitals overlap to give the sigma bond here between C and C. Work on those in your groups for just a few minutes. Doesn't matter which one's the main one. You're just stating 2 orbitals. Doesn't matter in order. What orbital does this H have? What does hydrogen have? Does hydrogen have 2 orbitals? Why not? Not because it's 1 electron inherently, but because it's in the first row. Being in the first row, hydrogen only has the 1 s orbital. It doesn't have 2 s. So this can't be the open up because this is First, determine its hybridization of both atoms, and then determine if you're reporting a sigma bond or a pi bond. Pi bond should be easy, P to P. Sigma bond is where you just name the hybridization. Kara's not convinced. Andy, do you think you have it? No? One more minute to discuss with your group, and then I'm going to pull you in.
Oh, that makes so much sense. Okay, I get it. Yeah. The double bond cancels. Well, what you're saying makes sense in my head, so if it's right,
All right, let's recap. What is an electron orbital? Raise your hand. We can't spend all this time talking about it if we can't remember what it is.
Where there's a 95% chance of finding an electron.
Okay, good start. 95% chance of finding an electron there. Can we add more to it? Sounds kind of the same where it is in space. I think you were looking for those descriptors. A mathematical equation that describes 95% of the probability of where they are in space. And that mathematical equation describes the size, shape, and orientation of where things are in space, of where the electron is 95% likely to be in space. So we are looking at bonds, which are overlaps of orbitals, which means now electrons have even more space that they can be found in. Space that now spans nuclei, not just surrounds one nuclei. And those size, shape, orientation features of the mathematical equation, those things are distinct for s orbitals, p orbitals, sp orbitals, sp2 orbitals, sp3 orbitals. So it is useful to know, are my electrons in the pair found in the overlap of orbitals that are both s, orbitals that are both p, orbitals that are both sp3, one s, one sp2. It's important to know that because now we know the size, the orientation, the shape. So, what orbital does carbon have to make its bond here? First, what is the hybridization of carbon here? sp3. It has 4 sigma bonds, 4 unique bonds to it. So what orbital does it have for making a covalent bond? sp3. What orbital does hydrogen have for making a bond? Only s. Hydrogen being in the first row has no p orbitals. Hydrogen cannot hybridize. So the bond here is the result of s to sp2 overlap. Or sp2 to s, all the same. Okay.
wait, isn't it SP3?
I'm sorry.
Yeah. Oh, I was like, wait, hold on.
I don't know what I was doing there. Thank you for catching S to sp3. What are the two hybridizations of the carbons making this bond? Good. We already determined one of them is sp3, and we already determined the other is sp2. So their sigma bond is the result of hybridized orbitals, one hybridized orbital being sp2, one hybridized orbital being sp3. Now, I want to give you guys a short break, and what I'm going to ask for you to figure out is the hybridized orbital, the orbitals that are bonding between N and H. Why don't we take about 5 minutes to get up and move around and get your blood flowing again before I really hit you with the fun stuff. And in the meantime, I gotta swing by my office quick. You know what? That was my next guy. All right. What did you find out? Nitrogen to hydrogen in this molecule. Yeah? You think it's the same as the carbon, that I just give you the same orbitals overlapping again? She said it more confidently. You're right. Hydrogen only has S. So any option that doesn't start with S in it is not right. But that nitrogen is not sp hybridized. It's not using an unhybridized p orbital. It has 4 electron regions, one of them being a lone pair, so you can think of that as similar to a sigma bond. 1, 2, 3, 4 electron regions, sp3 hybridized. Now I know that this molecule is kind of small, so I'm limited on giving examples about like a lot of different hybridizations overlapping with different hybridizations. But also, this molecule is a little clumsy to draw. Look at how big it is. And I even abbreviated parts of it. I didn't draw out that whole CH3 group. I decided you are probably smart enough to figure out that carbon wants 4 bonds, and there's 3 other hydrogens that can satisfy 1 bond each. So I condensed it a little bit. And right after this next segment, we're actually going to talk about assumptions that we can use to communicate structures even faster, because this is just going to slow us down. But first, did you know that valence bond theory sucks? And I'll prove it. Let me give you an example of an organic reaction. Very small, very quick. This is H2C double bonded CH2. Over my reaction arrow, I've got HBr. And my product is CH3CH2Br. Can you tell me something that has happened in this reaction? Okay, can we rephrase that in terms of bonds? We broke the HBr bond. Oh, okay. What else did we break? We did not break an H2 bond. Okay, it might help if I had drawn this a little bit differently. I'm going to draw this as H3C CH2Br. I broke the carbon-carbon double bond. So in terms of being a double bond, did I break the sigma or the pi? How do you know that? Well, sigma's still there, right? Sigma is there on the left, so is pi. Only sigma is there on the right. Every single bond is a sigma bond. Only double bonds have pi. So, broke the carbon-carbon pi bond. And what else did I do? I formed what? A C2H bond and a C2Br bond. Okay, so I broke HBr, I broke carbon-carbon pi specifically. I preserved carbon-carbon sigma. Why? Why does the pi bond break and not the sigma? Why can't I preserve the pi bond and break the sigma bond?
Pi bond's easier to break.
Oh, okay. Jackie says the pi bond's easier, so just break that one. It's easier.
It's the way that it's laid out. Because it's side by side and not head on, it's easier to separate that than this.
This is a really common explanation. The pi to pi bond doesn't overlap as much. Their electron regions, their mathematical regions, just don't touch much. So it's easier to separate them because of that. And that's fair, but then I would argue you're also getting all of it on top and on bottom. I don't know, like, have you done the calculations to see how much overlap they really have? Are we just taking it for granted that we say break the pi bond first, it's easier? To an extent, I think we do. But there is actually another way of representing bonds that energetically tells us why the pi bond breaks easier. Energetically proves it to us. And I'm not going to make you do the math, but I'm going to look at those drawings with you. Now, valence bond theory posits that covalent bonds exist because of the overlap of atomic or hybridized orbitals. But it doesn't get everything right. It gives us to a point where we can look at drawings and explain stuff about it, but it doesn't explain everything. So introduce molecular orbital theory. In other words, MO theory. Those aren't words, those are just letters. Molecular orbital theory says bonds are not the overlap of orbitals. Bonds are new orbitals that now span a molecule. It's not two orbitals that center on a nuclei overlapping. It's a new orbital that spans two or more nuclei. So, do you remember how we got sp orbitals, sp2, sp3? What did we need to do with the mathematical equations? Sum them. Add them together. And regions where the equations have different signs, cancel out. That's what molecular orbital theory does. But now, with the orbitals that we said are just overlapping. Doesn't that look a lot like how I drew the formation of our hybridized orbitals? I just drew them overlapped, and then I said, here's the new mathematical equation. So MO theory often works on diagrams. On the left hand, we'll draw this arrow to represent energy. An MO diagram has three lanes, three things that we're considering. On the outside are atoms. I'm going to start us with just hydrogen. Imagine the atoms on their own. What orbitals do they have? Just one s. Now, in the center lane, imagine the molecule, H2. Why is it H2 actually stays together? Why does a bond form? What is it about being bonded that holds them together? Why does helium-2, He2, not form a bond? When these atomic orbitals come together constructively, they actually lower in energy. I'm sorry, you guys probably saw that I was way off on my energy there. I go from having these orbitals on their own to having one big orbital. Two spheres overlapped, summed together to give me this oval. Kiara, how many nuclei in here? Yeah, nuclei, one. How many nuclei here? Right, both of the hydrogen nuclei are now located in this one new orbital. Remember, when we took S and P and made a new orbital, we called it sp, a new type of orbital. We're going to name this orbital as well. Because this orbital gives us a sigma bond, this orbital is called sigma. And if you ask me, somebody probably should have been that creative when it came to naming hybridized orbitals as well. I think a lot of students get tripped up because they don't understand what the difference is between S, P, and SP. They should have named it something cool like Jeffrey. If these two orbitals are out of phase, if one hydrogen's orbital is plus and the other one is minus, they actually come together destructively. They cancel each other out in the middle, and so they create these two half moons. It looks a little bit like a p orbital, but a weird shape. One shaded, one not. A node in the middle. And this orbital exists at the same time as sigma, but obviously would describe electrons of much higher energy. If electrons occupied this orbital, you can see how drastically higher it is relative to the atoms on their own. It would drive the atoms apart. It would break the bond. So we call it not a bonding orbital like sigma, but an anti-bonding orbital. And we call it sigma star. That's to say that if electrons occupy it, that bond breaks. Now, each hydrogen comes with one electron, so I'm going to put that in their atomic orbitals, and they're going to come together to pair, so I'm just drawing them with opposite spin. Where will these electrons go to? Sigma or sigma star? Sigma, because we always fill lowest energy. So why does H2 exist? Why don't those atoms just drift apart into hydrogen radicals? Because together, they create a more stable molecular orbital. That holds them together. They're lower in energy together. Now, helium is of nearly the exact same situation. If you don't want to draw this out, that's okay. I'm just going to quickly sketch this. We can get sigma and sigma star for helium, He, He, He2. But helium has how many electrons on its own? 2 electrons. So they both bring 2. Now I have 4 electrons to fill in this molecular orbital. When you look at the net energy, let's call this net 0. I gain some stability, I lose some stability. These 2 orbitals cancel each other out. These 2 atoms, He2, they don't know they're bonded. If you were to create this, they would just drift apart. That's why helium doesn't bond with anything else. There's no gain to it. There's no stabilization. Now here's something really weird. You all probably know the Lewis dot structure for diatomic oxygen. Can you guys tell me if you know what it looks like or not? Diatomic oxygen, O2. How many bonds between them? A sigma and a pi, a double bond. Here is what the MO theory says for O2. Your Lewis dot structure says sigma bond, pi bond, 2 lone pairs on each atom. And then you cool down diatomic oxygen, you bring it to a liquid, you condense it out of the air, and it is magnetic. If you drain liquid oxygen past a magnet, it gets pulled towards the magnet. Why? What about these paired electrons is magnetic? Nothing. The only thing that's magnetic is an unpaired electron. That's why it attracts a pair. MO theory says that the s orbitals on oxygen create sigma and sigma star and cancel each other out. The p orbitals on oxygen create sigma, sigma, pi, sigma star, pi star and sigma star. When I said sigma and sigma star. It's actually a lot more complicated than just two lines filling their octet. Notice that oxygen has a sigma orbital, two pi orbitals, and then it's got the equivalent of a pi star orbital. In other words, it breaks apart one of its pi bonds. Molecular orbital theory says diatomic oxygen has two pi bonds minus one pi bond, which equals one pi bond. But then MO theory also says these electrons are unpaired, radicals, magnetic. So Lewis dot structures, valence bond theory, they can get us to a good approximation. MO theory agrees one sigma, one pi, but it agrees in a different way. It got there by a different way. Weird stuff. Okay, now you're not going to have to work that hard at drawing these, but I do want you to recognize how we get those pi bonds. Why we can look over there and say, this is why pi broke first. So in this energy diagram, I want to take an sp2 carbon on either side. And if I can give you any advice, make this tall and give yourself space. In the middle, we're going to show the double bond between these two carbons. Would you guys agree that these two carbons are also bonded to two other things? Here and here. That satisfies their 4 bonds. That's going to make them neutral. Now, the orbitals that my sp2 hybridized atoms have, can you tell me what they are? What orbitals do they come with? No sp3 orbitals on an sp2 carbon. sp2 orbitals, how many? 3 of them. spp, 3. Are those higher in energy or lower in energy than p orbitals? What's higher, a p or an s orbital? P is higher in energy. So what would be the result of hybridizing S and P? It's going to fall in between, right? So these orbitals have one p orbital. I didn't give myself enough space. One p orbital and 3 sp2 orbitals that lie lower in energy. This is how we got here by hybridization. These bonds that go to other things, sigma bonds, right? So what orbitals are being utilized in these bonds that go to other things? The p orbital or hybridized orbitals? So those hybridized orbitals. So this carbon is using 2 of its hybridized orbitals to bond to other things. And this carbon is using 2 of its hybridized orbitals to bond to other things. So I'm going to ignore those from this molecular orbital diagram because I'm paying attention to the carbon-carbon double bond. Now, Jackie was right that head-on overlap between orbitals does create a lot of overlap, which means when these head-on hybridized orbitals overlap constructively, they gain a lot of energetic stabilization. And when they overlap out of phase, they have an equally high destabilization. Very low, very high. This head-on overlap, that's what gives us sigma bonds. So now MO theory is saying this is a sigma molecular orbital. But remember that these orbitals look a little bit like this. So when I get two of them that overlap, I get this weird big lobe in the middle, and then these little ears on the outside. That's my sigma molecular orbital. How many nuclei in that orbital? Both carbons. When they come together destructively, sigma star, it's actually just going to look like two sp2 orbitals pointing away from each other out of phase. Because in the middle, they were destructively interfering, and that makes them out of phase from each other, pointing in opposite directions. A little bit different than my hydrogen, because I'm working with things that are a little bit more complicated than just s orbitals. P orbitals, they don't have that same overlap, so they don't get as much stabilization, but they don't lose as much stabilization. All I'm doing with these lines, by the way, I'm just showing you where these orbitals are coming from, where these molecular orbitals are coming from. Now, in my opinion, not drawn super well. I apologize for the clutter. You can see that this is challenging. When these two p orbitals overlap side to side, they just make one big fat p orbital, which is actually a little hard to draw. So most people just preserve the idea of two p orbitals next to each other in phase. But these are not two p orbitals, they're one. They're one molecular orbital. And they create a pi bond, so they're called a pi orbital. And when they overlap out of phase, then I get what looks like two p orbitals out of phase from each other. Their shaded regions are opposite. And this is given, can you guess? Did I say it? Pi star. MO theory isn't useful for drawing big structures. MO theory is useful for understanding why bonds hold atoms together and how to break bonds. Now let's fill in some electrons. This carbon on the left comes with 4 electrons. This carbon on the right comes with 4 electrons. Keep in mind, some of these electrons, those are useful for going to other atoms. So I'm looking at 1, 2, 3, 4 electrons to fill my diagram with. Just these sets of electrons. So I'll fill from lowest energy, I'll pair, and then I'll move up in energy. Sigma, pair, pi, paired, done. I'm out of electrons. Now let's say that I start pushing this molecule around, and that carbon-carbon double bond wants to do something. Which electrons are the most at risk of trying to seek a new home, a lower energy place to be? The pi electrons. They're at the highest energy. If anybody wants to leave, it's the pi electrons. So why did the pi bond break? They're the highest energy electrons. We actually have a name for this. So this right here, this molecular orbital, it's called our HOMO. Bet you can't guess what that stands for. Highest occupied molecular orbital. Fun. The HOMO is the highest energy electrons. This is where electrons come from. These are the electrons that leave from a molecule. So which pi bond is most at, which bond is most at risk of breaking? Pi bond. This here, pi star, that's our LUMO, our lowest unoccupied molecular orbital. If electrons are going to come into my double bond system, they will look for the lowest unoccupied place to go. That's my pi star. This is where electrons will come to. And if pi star gets occupied, what happens to the pi bond? It breaks. So we actually have two justifications here. Either the HOMO left the double bond and that's why the pi bond broke, or the LUMO got occupied and that's why the pi bond broke. Valence bond theory cannot give you that. Valence bond theory says there's a p to p overlap and there's an sp2 to sp2 overlap. Cool. But valence bond theory cannot tell you why one of those bonds breaks over the other. MO theory says pi bonds break first. Sigma bonds are both more stable and harder to break. This is the justification. We are explaining a molecule's reactivity. You guys okay with that? I love MO theory. I know it gets cluttered, but it's kind of beautiful.
Can I just say something? You just explained that better in one class, and I think the general chemistry 2 teacher explained it in one month.
Thank you. That's my
like
goal.
Genuinely.
But if I can say, you had a foundation that I can build on.
Like
I didn't have to be there to give you that
was
foundation.
so much better of an explanation.
Some of these students were there when I taught Gen Chem 1. So do you feel like I did the orbitals justice the first time around? Maybe, maybe not. Did you learn MO theory in Gen Chem 2? How many of you took Gen Chem here at Slick? Okay, about half of you. And then how many of you learned MO theory in general chemistry? Yeah, so the people that didn't take Gen Chem here, predominantly. We don't teach MO theory in our Slick general chemistry. It's optional. I often don't because I'm pressed for time, but I'll throw this up there and I'll say, there's cool stuff, we don't have time, you're not being tested on it, moving on. And to be fair, I don't test much on this. I find it really hard to make these questions. But I'm gonna keep coming back to it. We're gonna use it as justification. You'll see one question for it on this weekend's unit test, and it is very simple. Like if you get confused by it, it just means you weren't reading it. So this is a big justification of why molecules behave the way they do. Okay, that went a little bit longer than I wanted to, but I appreciated you guys engaging with that. Now I want to talk about how we can simplify structures. MO theory actually makes structures really, really hard to draw. But let's compare how we can take this Lewis dot structure that we had for alanine and how we can simplify it into something called a bond line structure. And then we're going to try to simplify it even further. And sometimes this makes it more simple, sometimes it doesn't. But we're going to look at the condensed molecular structure. So honestly, if you don't want to redraw this, I don't blame you. But I'm going to draw alanine, and I'm actually going to draw every single one of its sigma bonds. please, actually, like, copy down later if you want to, because it's just so much. It's literally a waste of time. Would you agree? Like, what information does that give you that is useful? It tells you every atom explicitly. It tells you every bond explicitly. Tells you all of the lone pairs explicitly. But if we draw all of our structures this way this semester, you will draw about 10,000 hydrogens bonded to carbon, oxygen, and nitrogen. Are you prepared for that? I'm not prepared to grade that. In fact, you have assignments this weekend testing you on your ability to move out of that system and move into this bond line. Here is what alanine looks like in bond line structure. Clean, fresh, small, but it has a lot of assumptions. So I'm going to give us the assumptions. Rule number 1, and we have to agree on these. They're not my rules, I just enforce them. Rule number 1, assume carbon at every end and bend. I can't take credit for that. End and bend was given to me by a student. But we assume a carbon at every end and every bend unless it points to another atom. So this bond ends at a nitrogen. There's no carbon there. Ends at an oxygen. Ends at an oxygen. Nothing there. How many carbons? Here's an end. That's 1 carbon. Here's a bend. Here's another bend. 3 carbon atoms. Rule number 2. Assume hydrogens on carbon to fill an octet or to match charge. Because remember, carbon with a positive charge doesn't have an octet. Carbon with a negative charge has a lone pair. So we add hydrogens to carbons only to fill its octet or to match the charge that it has. Here's a carbon. It has 1 bond explicitly shown. It needs 3 more to have an octet. 1, 2, 3 hydrogens. CH3. Here's a carbon. How many bonds are explicitly shown? 3. How many more does it need to fill an octet? Just 1. There's 1 hydrogen attached to that carbon. Rule number 3, you may assume lone pairs. But, big but, you'll notice that I have not shown lone pairs. You may never assume charges. Maybe we should say that a different way. I don't want to say it like it's a prohibition on it. Let's change it. You must always show charges. You can assume lone pairs. You cannot assume charges. Without charges, I can't figure out how many lone pairs there are. What's the difference between a carbon with a positive charge and a carbon with a negative charge? A lone pair. So if I'm assuming lone pairs and charges, I would never know if that carbon has a lone pair or not, or has a hydrogen that's bonded there and it has a filled octet. Rule number 4. Must always show heteroatoms. Given that organic chemistry is the study of hydrocarbons and their derivatives, what are the most common heteroatoms you'll come across? Give me an example. Oxygen. What else? Nitrogen. What else? Sulfur. We're not going to see it that often. Phosphorus. We won't see it that often. Halogens. We will see very often. You cannot assume these atoms. They have to be shown. And lastly, must always show hydrogens on heteroatoms. Notice that I did not put a line down to N and then have you assume that there were two hydrogens and a lone pair. I told you it's NH2. Notice that I didn't have a line that went to O. I told you it's OH. We cannot assume these hydrogens. Which hydrogens can we assume? Hydrogens on carbons. That's it. Good? It's really going to make our life easy. But it takes a while to get used to those rules. So I encourage you to try going forward and backwards a few times. Take bond line structures, draw in all the carbons, draw in all the hydrogens. Throughout the semester, sketch in the hydrogens that we're assuming. They are the peskiest ones. They trip up a lot of students. Get used to these rules. Now, condensed molecular structure, we can talk more about this on Wednesday, but it's really not too hard. Don't show a lot of bonds. So this alanine becomes CH3, CH, CO2H. And off of the CH, I have to have this line coming down to show the NH2. I've condensed that whole structure into just one line with one little branch coming off of it. Now here, I'm not actually assuming any atoms. I'm showing all of the atoms explicitly. What I am assuming is a bit of the structural connectivity. What's going on with that CO2H group? How are those atoms all connected? That's not explicitly stated.
Is that just assumed to be like the functional group? Is that what's happening there?
Yes and no. When we come back in on Wednesday, I'll actually give you a few examples of bond line structures and their condensed molecular structure that I want you to be familiar with before we even get into functional groups. I don't like condensed molecular structure much, but there are some compounds where it's useful. For instance, think about methanol. That has a condensed molecular structure of CH3OH. Now try to do the bond line version of methanol. Okay, well there's a carbon and an OH group. In my opinion, bond line of methanol, not useful. The condensed molecular form of methanol, much more useful. This is how we're going to communicate all semester long. Bond line structures and a little bit of molecular condensed structure. So I want you to get used to it. Keep practicing. I have old study materials from when I used to assign my own physical homework. It's at the bottom of our modules tab. Go to that tonight. Go to it tomorrow night. Find examples that train you to draw bond line structures from Lewis dot structures. Get familiar. Look through all of it. Look at all the different bond line structures that you're going to see. All of those organic molecules you submitted, almost every single one of them, already drawn in bond line structure. Go look at it and figure out how many carbons are there, how many hydrogens are attached, what's the molecular geometry, what's the hybridization. Go apply today's learning to your compound. All right? When we come back in on Wednesday, it's section 2. Have a great night, guys. See you then.
Thank you.
You're welcome.